seems that we're back to spintronics-ish. Okay, so our last lecture will be given by Kerem Camsari. Is that correct? And he's going to share with us his experience in like pbits, or probabilistic computing with pbits, optimization, machine learning, and quantum simulation. Let's welcome Kerem.
Thank you very much. So I stand between you and the end of the summer school. But I'll try to make it, this was the original title, but I put, this is intimidating. So I put tutorial and I really changed it up, okay? So normally, this is a class I have in Santa Barbara. I would take 10 weeks to go through this material. We'll try to condense it to an hour. But I promise I'll try to give you a flavor of what this is all about, okay? And why magnetism plays such an interesting role in this field. And so let me start with a question. So how many of you have heard of qubits by show of hands? Okay, many of you have heard of qubits. How many of you have heard of pbits? Okay, very good. A subset of you have heard of qubits. So this is, they don't put it like that, but there's really these bits and qubits, they lie on a spectrum. Okay? So the bit is something you learn in, I don't know when you learn it, in high school or whatever, right? This is this idea of a Boolean object, which is 0 or 1, right? And that's basically everything that you respect in your life that differentiates you from living in the 40s, for example, is because of bits. Right? And if you take electronics out of your lives, digital electronics, there wouldn't be much left, really. It would be like living at the beginning of the 20th century. Okay? And these days, do you know the latest number? How many transistors that represent bits? How many transistors do you think are in NVIDIA's latest chip by order of magnitude? Does anyone know?
6 billion?
Billions are kind of low these days. They're talking about a trillion transistor. Phil Wong, Chi-Feng's ex-colleague, he was writing an article in Spectrum talking about a trillion bit transistor. It's crazy, right? So that's what we've been building, and they all represent bits. Now, many of you have heard of qubits. Qubits are kind of weird. Okay, so just to explain it, you find yourself in a technical discussion. Okay, the superposition of 0 and 1. What does that mean? Is it 0 and 1 at the same time? Well, not quite, but it's kind of like that, right? So it's not easy to explain, but then nonetheless, people believe in the power of the qubit, right? And there's a lot of, at least big companies left in this field that are trying to build these quantum computers. Now, why is this on a spectrum? What kind of spectrum is this? Well, in some sense, the bit is kind of a complicated object if you start from the first principles. Okay, qubit could be something like a single spin, for example. Okay? And the first thing you learn in quantum mechanics is what? Is that it's probabilistic, right? So even if you know everything there is to know about a quantum system, measurement involves probabilities and so on. Right? But if it is probabilistic, to give you a magnetism example, if you take a magnet which has 1,000 or million spins, right? 100 million spins. If you strip away those spins one at a time, and then you end up having with, if you're left with a single spin, then that would be a quantum object, right? The big magnet was a bit, which was in the hard drive. Single spin is a qubit. But the thing is, in that journey of stripping away electrons, you would go through a region where you have maybe 1,000 spins or 100,000 spins. And in that case, you would have something like a p-bit. Okay, that would fluctuate between 0 and 1 because the magnet would have so few spins at some point that it couldn't hold its state against thermal noise. Okay, so that would be a p-bit, and that's it. So make no mistake, if you know quantum mechanics, this is not going to be phase coherent. Okay, we are all, some people want to make that point as quickly as possible, especially my colleagues at quantum. Like, please admit that this is not going to be a quantum object. It is not going to be a substitute to quantum bits. But as I've been doing this, doing this for the past 10, 15 years, and now I feel like it's much closer than people think. That it's actually very hard to articulate what it is that a qubit can do that I couldn't do with a pbit. And I'm willing to have long conversations about that with you, okay? But the thing is, this is not a replacement for a bit or a qubit. This is a domain-specific thing. What that means is, just like the TPU isn't, NVIDIA's GPUs aren't going to change your day-to-day computing laptops, this is not going to change. This is going to be some specific domain that it'll be useful for. Okay, so that's the idea of domain-specific computing. And over the years, we've made connections to applications that are targeted by this noisy intermediate scale quantum computers, and also machine learning. Okay, I'll try to give you a flavor of all of those, but today it's a tutorial. I'm going to keep the research to a minimum. There's a lot of papers that you can read later, but today is about getting the basics. So there's a very wide application space. You know, the important thing that I view as doing research in computing or developing some sort of hardware, it better help a few things rather than just one thing, right? I mean, think about the GPU and what it enables, right? Like you can have a million machine learning models and still the GPU is going to be helpful for them, right? So the pbits, we've been looking over many applications over the years, and one thing is this, of course, P is for probabilistic. So one thing is for random number generation, okay? So when I bring this up, sometimes people say, oh, random numbers. I know random numbers. I can get you a million random numbers in Python. Yes, that's true. You could do that very quickly. But for some of the applications, you're going to need a few trillion in a few seconds, okay? And there's very good applications like that. So this massive amount of random number generation is by no means a solved problem. It's very difficult, actually, to get something that kind of looks random in CMOS at that kind of rate. Okay, and I'll show you examples where you need, let's say, 100 trillion random numbers just in a few seconds to solve some problem. Now, the other thing is, this is becoming more and more popular these days, this idea of energy-based models. So machine learning takes a lot of inspiration from physics. And in fact, physics of magnetism. It's kind of amazing that the knowledge that you have, the worldview of a magnetician, and people like you, is actually very useful. Sometimes you come here and they talk about spins and magnets, but in some abstract space. Okay, so it's very interesting. So there's papers there. You can see that it's like these machine learning, these energy-based models are targets of this probabilistic bits and so on. This has become a very big field now. There's now government programs in the US, you know, in Europe, everybody has a hardware for these tough, difficult problems, these combinatorial or discrete problems, like arranging a wedding table, for example. Like there are people who like each other, there are people who don't like each other, and you have to kind of make an arrangement and have a happy final arrangement at the end. Right? So that would be an example of a scheduling or partitioning problem or something like that, okay? And the view of a physicist for these problems is something like this. You have a cost function, which is or energy, that's better for us, right? So we have an energy in the y-axis. We have all these possibilities of arrangements, and then you're trying to find the best one. But there are some local minima. There's some local minima that you might be happy with, but maybe there's a better solution. So your goal is to probabilistically kind of search through the space and find a good solution. Right? So you can see the relevance of a probabilistic algorithm in such a picture, right? If you're here, for example, if you just told this blue ball just to sort of decrease energy, pretty soon you'd be stuck somewhere, right? So that's not a very good deterministic algorithm. You should make some mistakes. You know, the life slogan that I have for this is, it has to get a little bit worse before it gets better, right? So that's something you hear, right? So that's actually about local minima. You know, you have to kind of get out of your comfort zone for it to get eventually better, right? So things like that. Now this is kind of, if this is your first time of seeing this almost doesn't belong here, right? Because I just told you a p-bit cannot be a substitute for a qubit, but it turns out, you know, it kind of can in certain contexts. This is far too technical for me to get into, but let me just say that there's a very good class of quantum systems, legitimately quantum systems, that you could emulate with p-bits. And the math and the ideas there is very interesting. And you can do this people have been doing this in software. And today I'll try to show you, give you a hardware picture. Like, can we have a building block that will help us with things like that, okay? And this is something maybe we might get into later. Okay, so that's enough. There's more AI applications. This is a nice chart. You have this on your slides. You can go look back on it. Okay, so let's get on with how it works, okay? So a p-bit is a binary stochastic neuron. Now, sometimes this feels like, you know, trading something that you don't know with 3 other things that you don't know. If you know a little bit about machine learning, it's this idea of a neuron. It's a building block, okay? Okay? I mean, it has nothing to do with biological neurons Professor Ravi was talking about. Okay, so this is a far too simplified generalization. And stochastic is interesting. So we have probability in the update rules. We have probability built in. And binary is also interesting. We're always going to be 0 and 1. So here's a picture that you might recognize. This, the original, the way we started with this was the SOT that Professor Pai discovered with colleagues, right? So that's actually an MTJ sitting on top of heavy metal. So that's how we got into this. But now it has become a sort of an abstraction. So if you want to think of it like that, you can think of the I sub I as some current, and the M sub I as the state of the MTJ, for example. But for this discussion, I'd rather keep it general. Okay, it's an abstraction. You have an analog input, and you have a digital output. Okay, so that's it. Okay, so how it works is, if the analog input is 0, your device is to produce a random bit stream of 50 up, 50 down probabilities. As a function of unitless time, we're going to add time units to that time later, but for the moment, this is what I want. Now, it better be, it's very natural to think about it as continuous time, but you could also think of it as a flip. For example, you're rolling your dice, another time, another time, another time. People have proposed pbits like that too. But I like to think of it as continuous time, something that fluctuates on its own without any intervention on it autonomously. Okay, so that's it. Now, you can change that input, and your device is to show a property like this. If you have a positive or negative input, the duty cycle of the stochastic oscillation should change. Okay, that's it. Now, of course, I need to tell you, I need to relate this +1 to the duty cycle. Right? Oh, by the way, if you wait for a long time, this is what you get. If you wait for a long time, this is what you get. If you wait for a long time, that's what you get. Right? It's very, very simple. And now you can think of it as you can take it as an experimentalist. And if I give it to many of you, what would you do? You would probably sweep the I sub I and observe the behavior of the device. Right? So that's what you can do numerically. So if you sweep your current, dimensionless at the moment, from -4 to +4, you should see something like this. That you're pinned on one end, at some point you start fluctuating, and at some point you get pinned again. Now the red line that you see there is somebody who waited there for a little bit and took an average. Okay, so that's kind of a different experiment. The red line is sort of a steady state experiment, right? And the way we designed the pbit, we'd like that to have this sigmoidal shape, which is super important in physics. Machine learning took hold of that sigmoid, but it started with physics, actually. It starts with the physics of the Boltzmann law, StatMech, and so that's where the exponential comes from. Because a sigmoid is an exponential that sort of saturates. Okay? So that's the pbit. Okay, so how do I make one, right? I mean, well, there have been many proposals over the years. In the past, I don't know, 7, 8 years, anybody who has a noise source has proposed a pbit. Okay, but the first obvious option is, and this is, whoever is working on computing, this is the first thing you ask. Can you do it with existing technology? Because I got 1 trillion transistors to sell you, right? If you can do it with digital CMOS, you should. And I'm going to show you where even with that 1 trillion transistors, it becomes a difficult deal if you want a very large scale P computer, for example. So that's the obvious one. So that's my suggestion to anyone and everyone who's working on computing. Your first benchmark isn't some exotic memristor, it's digital CMOS, okay? So, all right, so digital CMOS, I'm going to show you what it takes, how you build a pbit with digital CMOS, transistor technology. And then you can go, okay, maybe I can have analog designs, maybe I can have MTJs, diodes, memristors, photonic pbits and whatnot, okay? So just like a qubit or a transistors, there's many ways to build a pbit. There's no one way. I'm going to take a flavor of an MTJ and try to argue that it's actually the best way to do it. Okay? But that's it. This is the building block. This is the pbit. That's how it works. Okay, but you're talking about these computers and all these applications. How does that work? Well, here's a picture of how that works. So this is sort of a slice. It's kind of a neural network. As you can see, you've got some neighbors. These are your friends. And there's some weights associated with your friends. For example, this could be a trusted friend with a big weight on your thinking. And this is another friend, and everybody has their own fluctuation frequency. So just like, so it's kind of a physical system, right? You're fluctuating, okay? And what you do is you take your friend's inputs based on the weights that, based on the degree that you trust them. Now the good thing, of course, is this is binary. You either trust them, you either take that input or you don't. Okay, so this is 0 or 1 for the moment. And then you have your own biases, that's H sub I, that doesn't depend on anybody. And then you get a number. So you at this point in time, everybody is in some configuration. You trust them with some fixed weight. For the moment, let's fix these weights. We don't have to, but let's fix them. And then you get this input and you make a decision based on your friend's inputs to you. Okay, that's how it works. Now, this is kind of a deceptive picture because there's actually feedback in this system. What I mean by that is, this is you, but you're a neighbor to somebody, right? You're a neighbor to somebody, so that somebody could be talking to you, for example, right? But this all happens asynchronously and evolves just like a physical system, right? Just like a network of, let's say, particles interacting, whatever, right? So there's feedback. So that's how it works. That's the general thing. And we have these equations, okay? These are very simple equations. This complicated looking one is the one that I showed you in the previous slide. You take the sign of a random number, compared with some tangent hyperbolic, and then this is your so-called synapse equation that many of you in neuromorphic computing recognize that. But the one thing that's different with pbits is that these are binary. So it's not an actual multiplication. Much of NVIDIA's success comes from multiplying 0.6 with 0.333, right? That's a very difficult thing. Here it's just going to be whether you take the weight or not. It's just addition. There is no multiplication. That kind of is an important detail when you think about hardware. Now, what does this do if you evolve this system? If you're in condensed matter or in magnetism, you know that many systems can be described by an energy, and their steady state behavior would be given by what we call this Gibbs distribution or Boltzmann law. Okay, this is kind of a very general, very powerful technique in condensed matter. This is, most of the time you're trying to get away from this giant thing. And why is it a giant thing? Well, think of it this way. If I have, actually that's my next slide. If you have 2 pbits, you've got 4 states. That's kind of up, down, up, down. Okay, fine. And this is some distribution of those 2 pbits. Yeah, but then if you have 4 pbits, it becomes 16. 6 looks like, at some point it looks like a Chicago skyline. And then it's not fun to draw this anymore. Sometimes my students come back, they come back and they say, okay, I have a 64 pbit system, how do I draw the sigmoid? Well, good luck. I mean, it's going to be, you're going from 1 to 2 to the 64. So at some point you can't even draw this. But that is what's happening. Okay? This is the space we live in with 8 pbits. It's kind of crazy. And your goal in life with P computing is to identify, for example, the tallest building in town. And that looks very obvious if I show you the full state diagram like this. If you don't have the state diagram, that's actually NP hard. That's one of the most difficult things to do. You can't, because you can't enumerate them. You don't know your ground state. So your goal in life, the pbits, will try to approximate those high energy or tall buildings, high probability, I'm sorry, not high energy, right? In physics, low energy, high probability states, right? That's a minus sign I fight for. Okay, right, probability is exponential minus energy. Okay, so this is a, many of you know quantum computing, and this is kind of an anecdote that's a 40-year-old anecdote, and that shows the imagination of Richard Feynman, right? So he's credited to have started quantum computing, and if you read this talk that became a paper, he sort of introduces this idea that if you have a quantum system, maybe you should build a quantum computer because that's going to simulate itself. That's going to let, physics will do the computing for you. But in that paper, he has the same concept for a probabilistic computer. He says, if you're trying to solve a problem like this, which is probabilistic, maybe you should build your computer out of probabilistic building blocks. It's kind of amazing that, and many of these things that we've done and the connections are inspired by that. Okay, back to the tutorial mode. Enough historical anecdotes. So what is the simple? This is my by far all-time favorite P-circuit because I think it just takes you so far. Many of these ideas are actually, you can study that simple system and really understand. So this is, if you take anything from this, maybe it could be this piece in the next 2 or 3 minutes. Okay. So this is a 2 qubit system. It's actually exactly those 2 equations. They're just well hidden right now, but we've got the outputs that are binary, let's say 1 or 0. Let's forget units right now. And then this is the synapse, right? This is the connection. With some conductance, I'm connecting the output of 1 to the input of the second. and the output of second to the input of the first. Right? So it's kind of a feedback system. And G0 controls whether how strongly they are coupled. Okay, so let's start with G0 is equal to 0, which means that the circuit is open. So what do you expect to see if the circuit is open? There are 4 states. So what's the expectation? The expectation is that you should see all 4 states with equal probability. These are 2 random bits that are going 50-50 up and down. But you see, I've already done a trick, right? I'm plotting it in a weird way. I'm plotting it as a function of this combined thing, even though they're not talking to one another, right? The 1, 1 means that at that point they were just +1. The next instance, maybe they became 0, 0, and so on. And I could take a histogram out of that time trace, and I would see something like this. The system is in one of these 4 states as a function of time with equal probability, right? If I take a long time average. Right? It's kind of obvious. Okay, what do you think is going to happen when I turn on the interactions? So this is when it comes online. Okay, so this is if you put some finite conductance. Now, suddenly the system seems to have a preference. The system states now emphasize 0, 0 and 1, 1 a little bit more often. So what happened? Well, suppose you and I are connected. And I'm +1, I'm sending you a plus input. I'm saying, you know, I'm +1, this seems to be a good deal, you should also become +1. And what happens is, you receive a positive input, you become +1, and you tell me back, you know what, I'm +1, you should be +1, it seems to be a good deal. So when we are 1, 1, we seem to kind of get stuck there, we seem to like that, and we stay there for a little while. And then a noise blows over, you know, wind comes and, you know, I flip my state and I become -1, and now I tell you, I'm -1, you should be -1. So you see, they get correlated in this way. And this is the simplest example of how noise can get correlated. You're very noisy still. If I looked at one of these pbits, they're still 50-50. But the other one is kind of following you. So this is very, very important. This is the equivalent of entanglement in probability space. This is called correlation. Yes?
Professor, so if, I'm just trying to understand, to move from 1, 1 to 0, 0, the noise is doing that?
Yes. So from 1, 1 to 0, 0, all it takes is for one of the pbits to flip in the presence of noise, and then their input to their neighbor will now switch sign. And their neighbor might follow them. But you can see they also sometimes are in the 0, 1, 1, 0 state. So this is a function of how well they're coupled. Okay, so if they're coupled too strongly, then they'll be locked. You'll see this idea of a minima. But if the G0 is kind of weak, then noise will take over and make these things fluctuate. Does that make sense?
Yes.
Okay, very good. So this is when the G0 is positive. Now you can also play with these correlations. Imagine throwing an inverter in there. Okay, imagine throwing an inverter in there. Now what I've done is, if I'm +1, I'm telling my neighbor to be -1. You see, now I'm emphasizing 0, 1 and 1, 0. Okay? So this is the simple, as I said, this is the simplest possible P circuit, but you can just, this takes you far. You know, for example, if you can see the idea of broken symmetries, you know, lots of things, just by studying this simple example. So I think it's worth understanding it. And you know, in condensed matter, what would you call this? What is this? What have I done here? I've built something that you all know very well. I built a magnet. This is exactly how a magnet works. This is why, you know, because you have million spins and they're interacting, and the sign of the exchange interaction is, replace the G0 with J. Positive J makes a ferromagnet, negative J makes an antiferromagnet. So this is something you already know. But you see, the amazing thing now is now it's an electrical circuit, and I can engineer it in any way I like. I can make complicated magnets. Right? That's the story. Okay. All right. Okay. So let's move on. So now there's a tricky point. So I've given you this.
Professor,
oh, sorry.
I
Go
have
ahead.
one question. Sorry, I was confused with the time axis.
Yes.
The information passing from one to the other happens instantaneously.
That's a good point. Right now we're assuming that the magnet fluctuations are kind of slow, and this electrical circuit is quite fast. So information at this point, you can imagine that in fact, that's one of the only things you have to make sure happens in this case. The other one I'll mention, there's two things that need to happen. This communication needs to be fast, so that's a very good point. And there's something more, and I'll explain that. Very good point, thank you for raising this. Now what's the other point? So again, communication has to be fast. So if you put time constants here, this better be fast, the communication. That's kind of easy intuitive, right? Let's say you changed your mind. And I hear about, let's say we're trying to meet next week. And by the time you hear from me, the week passed. Well, we can't converge, right? I mean, you need to hear from me quickly so that you can respond to what I have now. So that's the point that your colleague was making. Okay, the second point is this. If you take this, you take a picture of these equations, go to GPT and have it implement these equations. Now, most of you learn in MATLAB, in Python, in all these numerical languages to do parallel updates, right? You think, you know, if I give you this, what you would do is you would, I'll get back to you in a second, you'll do something like this. You would start from a random initial condition, okay? And then you would write a for loop for time, and then you would say that, you know what, I'm going to compute a current vector based on the states of these pbits, right? And you would want to do it vectorially, meaning you would calculate an I given an m vectorially. And in fact, you would make fun of your colleague who puts another for loop here. Right? You would say that, you know, what are you doing? Like, you can get rid of that for loop. But if you do that, something breaks. And that's kind of very unfortunate, and it's also an opportunity. Okay? So what happens is something like this. Suppose they both started at +1, +1. Okay? And suppose the interaction was negative. This was an antiferromagnet. So remember, they're trying to disagree. They're trying to disagree. So I'm trying to disagree. I'm in the mall. I want to avoid your way. Like, you're coming at me. I'm trying to go the other way. You know what happens most of the time? You make a move to the right, the other person makes a move to the right. You make a move to the left, the other person makes a move to the left. So that's exactly what's happening here. So let's watch. So they're trying to disagree. They're both +1, +1. So the first one tells the second one, disagree. You go the other way. Get out of the way. So that's this -1 to your neighbor. But your neighbor also tells you to get out of the way. And then you both get out of the way at the same time. And what happens is you end up becoming -1, -1. Oops, you know, you're trying to disagree. You couldn't. And the next turn, the same thing happens again. And if you look at this system, you see these weird oscillations. And this happens every single time. And as a joke in my lab, when we give these equations to the beginning unsuspecting graduate students, we don't tell them. And they come back and they say, you know, I'm seeing these weird oscillations that looks like, you know, and 3 and 1 are these two states here, like plus, plus, minus, minus, plus, plus, minus, minus, okay? So this is a problem, right? Because if you're doing this in software, which it means that you have to update them one at a time. Remember, just a little bit asynchronous and it would have been gone, right? For example, if you just listen to me before speaking exactly at the same time, you would disagree. You would become -1. And you would tell me to become +1. No problem. Right? So this is a mathematical accident that happens because of the way we think in digital computers. But in physics, so why haven't you heard of this by now? Why doesn't a magnet show these crazy oscillations? It would be a cool thing to see. Well, the reason is in nature, nothing happens at the same time. I mean, even when you're speaking with a colleague, like you sometimes interrupt them, etc. You get, I mean, in the mall, you find a way to get out, right? I mean, so that's exactly what happens in physics because physics is asynchronous. And if you build these with magnets, we very often don't even think about this. This happens by itself. You don't have to do anything extra, which is amazing. Now I can take the question, yes.
Thank you. So I have a question related to previous slide.
Yes.
Actually, I couldn't get like how this, I think you were introducing this resistance in your circuit.
Yes.
So how it is changing the probability of happening any state?
So the resistance is fixed. It's not changing anything. What is not shown here is the oven, the noise in the system. There's noise. So even if there is some configuration, noise can knock them over. And if one of these pbits change state, you see the current that goes to its neighbor changes sign. So that's how they kind of will fluctuate over these different states.
And this NOT gate, when you are introducing this,
Right.
then what it is doing to noise?
It's not doing anything to noise. It's just when you're +1, now you're telling your neighbor to be -1. That's it. It's just changing the sign. Like this is when you disagree with your friend. This is when you agree with your friend. But you change your mind often. Friend changes their mind often. And then this is the result. Like this is, if you're in very strong disagreement, you'll see that, you'll see that 50% of the time you are 0, they are 1, and 50% of the time they are 1 and you are 0.
And just one more question related to this data. So this 0, 1 and 1, 0 state, it is having a bit probability, or it is like almost 0 probability?
Which one? These ones?
Yeah, in these two.
Well, that depends on the strength of this G0. As you go from 0 to something,
Yeah.
this histogram will start looking like this. So the bad states will go down and the good states will go up. That's related to the temperature, effective temperature of the system. And it's almost like a ferromagnet. This is above the Curie temperature, this is below the Curie temperature, and in between you can be somewhere there.
Yeah, but like lower probability state may happen. I mean like 0, 1, 1, 0.
Yeah, and here it is happening, right? I mean, it could be a small number. And yeah, unwanted state could be because its noise is too much in that state. Make sense?
Thank
Okay, perfect. Very good. Please interrupt, okay? This is, please interrupt and ask questions. Okay, asynchronous is important because if you do this, you get locked, and that's not good, okay? So that's a very tricky point. Now let's do something more. So simultaneous updates between connected pbits are not allowed. And I could tell you a little bit more about what I mean by connected and what you can do if they're not connected, but I don't have time, so let's kind of move on. Here's a slightly more complicated thing. AND gate, you all know what an AND gate is, but now it's with a twist, right? This is, again, this is my next favorite example. And we're going from like 1 pbit, we've done 2, now we're doing 3, okay? And usually in my group, in this field, there's a phase transition in beginning. Like they start with 1, 2, and 5, and then next week they're at 1,000. And the space is, of course, exponentially growing. But these are very instructive examples, in my opinion. So this is a 3 pbit circuit. Don't worry about how I got those G naughts, okay? So often people are curious about how you get those values. If you give me a truth table, there's many ways that I can give you the connection matrix. Machine learning is one. Linear algebra, whatever. Assume for the moment that you give me a truth table, I can build the circuit for you, especially if it's small, right? And I'm trying to make an AND gate. Okay, so how is this going to work? So let's say that we run this, and let's say that the G0s are 0, so very high noise, hot temperature. Right, so you've got now, of course, it's getting a little crowded to plot this, right? Now you've got 3 pbits and 8 states, right? So everything is probable. Right? And you compare it with something like Boltzmann law, they match, everything is probable, blah, blah, blah. Right? And you turn on the interactions, and you see now, instead of those 2 states, I've actually encoded the truth table of an AND gate. Right? 0, 0, 0. Right? The third one is the output. The first 2 are the input. So you all know this. 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So the system somehow it's a kind of a magnet or a spin glass that kind of learned an AND gate. The behavior between constituent spins are acting like an AND gate. Okay, it's kind of interesting, and when I show this to circuit designers, I don't know how many of you are into logic and things like that. People kind of scratch their heads and they say, this doesn't make sense. This isn't how we build an AND gate. What do you mean? Like, where's the input? Where's the? I want to put a 0 here and a 0 here and get an output. And we tell them, yeah, you can do that. You can use that bias term that we talked about to fix certain pbits. For example, you can go to A and B, and you can fix them. You can say that, okay, whatever your neighbors are telling you, you're going to be +1. And here's the bias, right? Because this is your neighbor's input. But you can just jam it, right? You can just put a +5 here. And remember the sigmoid, right? You can easily saturate one of those pbits or 2 of those pbits. And yeah, you can make it work like a normal AND gate. Input is 1, input B is 1, output is 1. Very simple. But the amazing thing with these P circuits or P AND gates is that you can do the same thing to the output. What I mean is, you can make the output 0 and ask the circuit, what are some consistent inputs with the output being 0? And that's kind of weird. But you see, this circuit finds the only possible consistent states with the output being 0, right? Look what it finds. It says that, okay, I'm going to be 1, 0, 0, 1, or 0, 0. And nothing else is allowed because the third bit is refusing to flip. So the others need to find consistent states. Now, this can look like a silly example, but what you're just seeing is factoring a 1-bit number. You actually found the prime factors of 0. It's 0 times 1, 1 times 0, and 0 times 0. Well, these are not primes, but you found the only way. You found all possible ways to write down a 0 in a multiplication. Okay? And that's what we call invertible logic. Okay, so this is a very important concept because what that means is, whoops, but what that means is, this is a very general way of solving inverse problems. For example, you want to factor a number, you just build a multiplier, and you ask the circuit, what makes you 15? And the circuit will have to find 5 and 3. Right? So you can build factorizers and things like that with this trick. That AND gate example is simple. And for any inverse problem, like there's in computer science, there's these satisfiability problems that you have a lot of constraints and you're trying to satisfy your constraints. You build the forward circuit and you operate it in reverse. Okay, it's kind of neat. And this is kind of we can do copy gates, AND gates, and we can compose these gates, these probabilistic gates. For example, there you're seeing AND gates are attached to an OR gate, and whatever it is, you get the right truth table that you want. But what that means is, just like a universal quantum gate set, you can have these AND gates, NOT gates, copy gates, NAND gates, whatever, and you can build whatever you want. Okay? So that's kind of neat. That's what we do. And here's a sort of a high-level example. This is state-of-the-art integer factorization. So you build a multiplier. Okay, so we don't have time to get into all this. But this is basically, all of you know this circuit. Okay, this is school book multiplication. And how do you multiply 11 and 15? You bitwise multiply, you add, and you shift, you add, you shift. This is that circuit in Boolean logic. But if I do it with pbits, now I can ask this question, what makes you 50? You clamp the output product to something, and then the circuit tries to find the consistent inputs with it. Okay? And with that trick, well, I mean, first of all, that becomes, I mean, just to tell you, this is a very difficult problem. This is an NP, non-deterministic polynomial time, which means it's kind of an exponentially hard problem, even for our best algorithms. And just to tell you what happens, that innocuous-looking schoolbook multiplication circuit that you all know becomes a network of 3,400 pbits. And this is the graph. This is the actual graph. These are all individual pbits. And who can tell me the state, phase space that I'm living in? I'm living in 2 raised to the power of that number. Okay, so there's that many possibilities that I need to now figure out. And one of them has my factor. One of them has, outputs a minimum energy. And, good luck finding that. Okay, so this is a highly advanced optimization algorithm with pbits. There's replicas here. There's notions of temperature. And you take only, you take about 1.2310 to the power 14. So 123 trillion flips, okay? That's how many states you need to go through to find that ground state, okay? So in this case, we're factoring this number, which I'm not going to attempt reading. I'm not a native speaker.